Testing, testing, 1, 2. Shut your mouths. Just kidding. Okay, so I already mentioned a little bit how everything's going to work together. We're taking balanced reactions and all the reactions, and we're starting to add math to them. That's going to require more things for you to keep track of. Eventually, there'll be a very dark time when you have to write your own reaction, then balance it, then do a bunch of math. Today and tomorrow, I'm just going to I'm going to give you balanced reactions and show you how the math works. Okay? The branch of chemistry that is responsible for kind of doing math with reactions is called stoichiometry. Stoich. Like that. As I mentioned, it's the branch of chemistry that's responsible for keeping track of quantities in reactions. Every reaction is like a blueprint or a formula to follow to make a specific thing or to produce something or to take something and break it apart. Okay? And the numbers that are involved in the formula, specifically the coefficients, act like sort of guide bars to get you to start to talk about math. Okay? Kind of like if I was going to build the easiest bike ever, let's say that one bike was made of only 2 pieces. Let's say the pieces were wheels and frames. Worst bike ever. How many wheels do I need for that bike?
2.
How many frames do I need for that bike? These numbers allow you to do all sorts of math. And the reactions work the same way. If I asked you easy questions like, how many bikes can I make if I have 20 wheels? You can do that math in your head, right? If I said how many bikes, if I got 20 wheels, how many bikes can I make? You'd take 10, 20 divided by 2 and have 10. But you could also do, if I had 20 wheels, something like this. Wheels. If I had 20 wheels, I could use these numbers and coefficients to write the problem out in the way that we've been writing out problems all year long. I would say 2 wheels down here. And how many bikes do I get from 2 wheels? 1. I just take this number from here. 1 bike down there. The end result is 10, yes. And notice wheels cancels out, and I'm left with bikes. And obviously, we all know 20 divided by 2 is 10. These numbers, which again you could do in your head with no problem, are going to be guides for us to do the same kind of math with chemistry, except we're going to use balanced reactions to get those numbers. Pretty good, right? Here's a balanced reaction we'll use for most of today. It's going to be ammonia decomposing to make nitrogen. And usually we don't write the ones, but we'll write them today because you'll need them, or you'll need to remember that they're there. And then it also produces hydrogen. Those are the 3 things that we make. These numbers here, these coefficients, they really mean 2 things. We learned that last chapter, or last unit, or yesterday, I guess, that they were there to balance the reaction out. But in reality, they sort of mean 2 different things. Here's one. Coefficients mean one, on a molecular level, they mean the number of molecules. So if you're reading this reaction in your head, at least when I read this reaction, I always say 2 molecules of ammonia decompose or whatever to produce 1 molecule of nitrogen and 3 molecules of hydrogen. That's what it means that's the way that it works. That's the ratio in which it happens. Just like the bike example above takes 2 wheels and 1 frame to make 1 bike, or if 1 bike sort of broke apart, as we have it written there, then it would produce 2 wheels and 1 frame. Same thing here. 2 ammonias always produce 1 nitrogen and 3 hydrogens. That's how you should read that. But we don't really deal with molecules that much because they're small, and you can't hold them in your hand, and you can't see them, and we don't have the technology in this class, in this high school lab, to be able to actually do anything with them, at least on an individual level. So the other way you can read it is moles. Moles is a whole bunch of molecules, and oftentimes a mole of something or more or less or in that neighborhood you can actually see or touch or feel and like actually work with in lab. So we used to say moles for this class is more important. So 1 mole of ammonia, which is a whole bunch of ammonia, decomposes to make 1 mole of nitrogen and 3 moles of hydrogen. That's kind of how we would treat it in this class. These numbers then can be used as ratios, which we call mole ratios, to actually do some math. So that's kind of what's next. You can use the coefficients as mole ratios. It's a pretty common word that you should make sure you know, to do simple calculations. The mole ratios allow us to convert between any product or reactant. Thank you. So a common example, or I guess the easiest example, example 1. If I asked you how many moles of hydrogen are produced from 3.6 moles of ammonia. Hi. Thank you. Much like the problem we just did above when we're talking about bikes, this can work the exact same way. For a conversion problem, if you forgot conversions, you always start with what you're given, which in this case is 3.6 moles of ammonia. Start there. And for any conversion, you want to cancel out what you start with and get to what you want to get to, right? Or get to what that question's asking. People don't like these because you have to read this question more than once sometimes, and teenagers tend to hate that because that's just a waste of time. So you have to go back and read it, make sure you know where you're starting and where you're finishing. Also, specifically teenage boys, not to stereotype, but it could be girls too, don't like these because you should keep track of what you're working with, and people like to not write things here or there. And I know the math is easy, but it's the process that we are trying to learn, because I'm gonna make it harder in about 10 minutes, so make sure that you know at least this part. So you're starting at moles of ammonia. The numbers come from the balanced reaction here. So I know from this balanced reaction that 2 moles of ammonia, again, from the balanced reaction, right there, that 2, will always make, which one am I going to? Read the question again. Hydrogen, right? I know that 2 moles of ammonia always make 3 moles of hydrogen, and the numbers here come from the balanced reaction, which I gave to you, but you can see in the future it would be a problem if you did not know how to balance a reaction, because then you could never get this problem right. Who is? That's convenient. Hi. Want to give me those? Thank you. Got it. So the math is not challenging, right? 3.6 times 3 over 2. Notice that moles of ammonia cancels out, and you're left with moles of hydrogen. I wrote the things in there because it gets confusing because there's not the same thing. This one's ammonia, this one's hydrogen. So make sure you write things down. It makes your life a little bit easier. What's 3.6 times 3 over 2? I know what it is. It's 1.2. Wait, no, it's not. What is it? 5.1? I did a different problem last hour, sorry. 5.4 what? Moles of. Don't be lazy. That is where people mess up. Because they get lazy, they think they know it. The math is not hard. Anyone can type in 3.6 times 3 over 2. The problem is you don't write stuff here, and then you don't know what this is supposed to be. And then you mislabel it, and I give you points off. Okay, so moles of hydrogen be the correct label. Want to try one? Sure you do. How many moles of, let's say this time, NH3 are required to make 3. I just did 3. Shoot. 3.5, it's totally different. Moles of N2. I should mention the last problem and even this problem. You're only ever looking at 2 things. I can ask you about anything in this reaction. This one right here, you can't see it very well. But I'm only ever focused on 2 things. In the problem we just did, all I cared about was ammonia and hydrogen. In this problem, all I care about is ammonia and nitrogen. So I don't worry about the other one that I'm not doing. You're only ever looking at 2, and the other one's not really that important yet. So what do you start with? No, you want to try it? You try it first. Take a minute. Try it. Do it. Write things down. Read the question again. Start with 3.5 moles of nitrogen and go from there. Sorry. I don't know. Yeah, oil. You have to decide where you're starting and where you want to finish. So you start with 3.5 moles of nitrogen. And that one's going to go on bottom. So you look back at the reaction. And on bottom it's N2, the coefficient's a 1. Okay, so you write 1 mole of nitrogen on the bottom. Right, so it cancels out. And you're going to, it says, ammonia, so you go to use that coefficient on top, which is a 2. 2 moles of ammonia. This mole ratio here tells you the ratio between those 2 things, in this case, ammonia and nitrogen. And the one you start at on bottom, the one you want to get to on top. And 3.5 times 2 is 7, yes? 7 moles of ammonia would be the correct label. Bye. Any questions? This is the critical step, because this is how things react. This is the ratio in which they interact. How often do I ask you to measure something in moles in lab? Have you ever measured anything in moles in lab? No, you never have, right? You always measure it in what? Grams. And so, more importantly, is to really start and end with grams. That's a different kind of problem which has more steps. Let's try a simple one first, right? Want to use the same reaction? That's the spirit. I'll rewrite it right here. Good. What if I said how many grams of N2 are produced from 5 moles of NH3? Question mark. What if I said that? Guess what I just did? What happened? We feel left out over here. They don't care. All right, if you're given grams or if you need grams, you have to do more steps. Okay, the mole ratio, the step we just learned, that's the most important step. But you have to convert either to or from grams to, depending on what the question asks. This question asks us to have our answer in grams, so we're going to have to convert at the end. You still start with what you're given, which is 5 moles of ammonia. Since I'm starting at ammonia, where does that go in the conversion factor? Bottom, great job. And the number is the 2 from the balanced reaction. So you use 2 moles of ammonia. And you want to get to, in this question, you got to read again, I want to get to nitrogen. So that's 1 mole of nitrogen. But I'm not done, because I want my answer in grams. Is there a way you can get from moles to grams? Yes, there is. OMG. That would be if you wanted molecules, you'd use 6.02 times 10 to the 23rd, which we will do eventually. But if you want to do just grams, you'll just use the periodic table and add up the molar mass of the one you're trying to get to, which is nitrogen right here. One nitrogen is 14 grams, but two of them would be what? 28. You get it right, of course. 28 grams of nitrogen here equals 1 mole of nitrogen down there. Yeah. It's okay. Oh, yeah. Okay.
So, like, when you're trying to figure out the mass, do you not use the, like...
Use the little number.
Well, I know, but, like, do you not use the 01 then?
No. What do you mean 01?
It's like 14 or 01.
Oh, yeah. You just, I mean, if you can round it in most cases to the nearest whole number. Yeah, great question. What's happening? Did you do this already?
Yeah.
What is 2.5 times 28? What is the answer?
70.
70, thank you.
I said it 3 times.
I'm sorry, I didn't hear you.
Obviously not.
What's the label?
Grams and
Don't forget the N too, that's important. So there's a more common problem. Yeah, go ahead. If you actually wanted to figure out a number in lab that you could measure, it would be grams, right? So this is actually a pretty common problem. It's not the most common, but it's pretty common. The most common is to start with grams of one thing and end with grams of a different thing. Guess how many steps that has? Nah, that's too many. 3. Here's a general rule for solving 3-step stoichiometry problems. If you're given something that's not in moles, you should always convert to moles first. The second step is always going to use the mole ratio. The mole ratio is just this part right here, the part where you actually use the moles from the balance reaction. Today and tomorrow, we're just going to start at grams of one thing and end at grams of another thing. But you can start anywhere or finish anywhere on, well, we don't have mole wheels, but you can start at molecules or finish there. You can start at volume or finish there, or grams. And we're going to start, today is mass, so we start mass of one thing and finish at mass of another thing. So, but the sun's coming out because you've just been enlightened by your teacher. Remember, you're on audio. Wait, why are you all laughing? All right, convert whatever. Convert whatever you want your answer to be in. All right, I get it. Convert to whatever you want your answer to be in. And you'll see what I mean in just a moment when I show you one last problem. We'll call it example 4. And it looks like this. How many grams of hydrogen will react with 112 grams of nitrogen? Question mark. So bright. Why? What's happening? Can't wait till what?
It's like nice out.
Oh, I know, right?
Well,
That's class outside.
Yeah, we can do it today if you want.
Do it right now.
Let's go outside. Maybe this weekend we can run in shorts. It'd be nice. About shorts?
Are you like nervous that you're getting recorded?
No, I don't really care.
Like, I feel like I'd be so nervous.
I'm not. It only goes up to YouTube for millions of people to see. Got a lot of followers. I think I'm in the 30s for followers. So get on my level. This problem is the most common kind of problem because you start with grams, which you actually can hold or measure in lab, and you finish with grams of something else. But you can't just convert grams to grams because this is not grams to grams. This is moles to moles. So you got to convert your grams to moles first, then use the mole ratio, then convert your answer back to grams. It's kind of a pain, but it's fun. Here you go. 112 grams of nitrogen, start there. This is the most common kind of stoichiometry problem. It's called a mass-mass problem, mass of one thing to mass of another thing. You want to convert grams to moles first based on my little 3 rules here. The molar mass of this has to go down here at the bottom, so that was, we just said 28 grams per mole. I've just converted my grams to moles, so now I can use the mole ratio from the balanced reaction. Go back and reread the problem. Where am I starting and where am I finishing? I'm starting at nitrogen, And I'm finishing at hydrogen. So use those numbers from the balanced reaction up here to do this. So 1 mole of nitrogen will always react with 3 moles of hydrogen. That is the ratio. If you wanted your answer in moles, you'd be done right now. And you wouldn't do this third step, but you want your answer in grams, so you got to convert back to grams. But now you're in grams of hydrogen because you canceled out moles of nitrogen. So 1 mole of hydrogen, what's the molar mass of H2? Don't overthink it. 2, it's right, because it's 1 plus 1. So 2 grams of hydrogen. When you solve this problem, you take 112 times 3 times 2 divided by 28. You know what you get? Get 24. It's good, right? The best part is we can do this for the rest of the year once we figure it out. Yay, there's a math the rest of the year. You're so happy. Every chapter will be different, or unit starting after this one, but we'll always have an opportunity to do some of this. Questions? Feelings? Want to be recorded for posterity?
No. Yeah.
I was going to say something, but I don't remember what it was, so bye.